Chem 106, Chapter 16, Lecture 3. There is the section on polyprotic acids and bases, which you won't have any lecture problems or exam problems over. But you should just understand that polyprotic acids, that means there's more than one acidic hydrogen. And the main point of this is that really you're going to have multiple Kas. For each acidic hydrogen, you're going to have multiple Kas, or for each one, you're going to have a Ka. So that results in multiple Ka values. The first ionization, the first acidic hydrogen to come off, has a relatively speaking large Ka value. The others, if there's 2 or 3 or 4 acidic hydrogens, the second, third, fourth, however many there are, those Kas become increasingly smaller. And even the second one is fairly negligible compared to the first one. So as long as we're just talking about equilibria and not titrations, the acidity of a polyprotic acid really is mostly just due to the acidity of the first ionizable hydrogen. The rest of them, their equilibrium values are so small that they don't really, within significant digits, affect it. Now, if you're talking about titration, you're going all the way to completion without view of equilibrium anyway, and that's an entirely different topic. The Lewis concept of acids and bases we will come back to in deeper detail when we talk about coordination compounds and all the transition metal complexes. But really, especially when you get to organic, the Lewis concept will eventually take over. You will use the Bronsted-Lowry theory insofar as talking about pKa values for the acidity or basicity of various things. But really, when you get to how organic chemistry works, you will be exclusively really using the idea of Lewis, where a Lewis acid is a substance that can accept a pair of electrons from another atom to form a new bond, and a Lewis base is a substance that can donate a pair of electrons. Because that's really what chemistry is all about, is the movement of electrons from one place to another. The valence electrons are the ones that do all the work, in chemistry at least. You have to, if you get into the core electrons, you're back to physics. But the valence electrons for chemistry are what do all the work, and Lewis, is the one that really helped define that and show how that all works. So again, like I said, we will come back to Lewis ideas, especially when we get into the complex ions or coordination complexes. That's another chapter, so we will come back to that. The next section on the common ion effect is going to have significance for both this lecture and lecture 4. But really, within context here, this common ion effect means that we're talking about a weak acid and its conjugate base. And so we're not talking about situations where if you just put a weak acid into water and you set up an equilibrium, because that's an insignificant amount or a very small amount of their conjugate base. That's not the same as saying we're going to mix a weak acid with a significant amount of its conjugate base to form a new solution. This common ion effect, where you have a significant amount of conjugate base and its weak acid together in the same solution, that is going to affect the pH significantly. And so what will happen is that when we mix a weak acid with a significant amount of its conjugate base, we create a solution called a buffer. And so section 10, controlling pH buffer solutions. So a buffer solution is a solution that is resistant to the change in pH when you add either strong acid or strong base to it. Now, bear in mind that we're talking about very small amounts. So especially if you're thinking physiologically, where in the blood the bicarbonate ion is acting as the buffer part of the molecule in the system that keeps your blood at a constant pH, and then there's phosphate that helps keep your cellular materials in check. So within cells, it's a phosphate buffer. Within blood, it's a bicarbonate buffer. But when we talk about it being a buffer, we're only talking about the addition of small amounts of acid or base, where then the system resists change. In lab, you're going to investigate making buffer solutions and the effect of adding acid and base to them. But in that case, that's a fairly significant amount where we will change the pH, but not as much as it would if it was just by itself. The acid or the base, how much they would change pH, how much they would change solution if the buffer wasn't there to begin with. All right, so with buffers then, two substances are needed, and a weak acid and conjugate base. And so when we mix these together, then we have this conjugate acid base pair. Let's see, and now without going through the derivation, because I did that for you in one of the discussions for the labs that you're doing, and so you can refer to that and see how this equation is derived from the Ka expression. When you look at anything, when you put a weak acid into solution, you generate a Ka expression. If you rearrange that and then take the log all the way through, you end up with the Henderson-Hasselbalch equation. This equation saves you from having to do ice tables. So this is a very nice equation that is very straightforward, and like I said, can save you from having to do ice tables, and in particular can save you from doing the quadratic equation calculations. But it must be understood, this equation, this Henderson-Hasselbalch equation, which again you need to commit to memory because you don't have it as a listed anywhere on the exam, you must know it from memory. But this equation, the Henderson-Hasselbalch equation, is useful only for buffer solutions. Do not try to use the Henderson-Hasselbalch equation when calculating an equilibrium situation of just a weak acid or just a weak base or whatever. The only place that you can use the Henderson-Hasselbalch equation is for a buffer solution calculation. And so the pH of that buffer solution is equal to the pKa value, which this is your real reference point. The pH of the buffer is going to be fairly close to its pKa value, and the second term, the log of the conjugate base concentration over the weak acid concentration, this is just a modifier. So really the pH is primarily dependent upon the pKa of the weak acid we're talking about, and the log of the conjugate base over the concentration of the weak acid. This is just a modifier term that can either make the pH go up if there's more conjugate base than weak acid, or it can cause the pH to drop if there's more weak acid than there is conjugate base. So all we're doing is using this to manipulate the pH of a solution to make it whatever we need for the kinds of experiments we need. Different physiological experiments, for instance, need different pH buffers to make them work. And so what we would do is choose a weak acid conjugate base, but the weak acid we would choose that has a pKa near the pH we need and is not toxic to your system that you're trying to investigate. So we need a weak acid that has a pKa value near the pH you need, and then we can manipulate the amount of conjugate base over weak acid to modify the pKa to give the pH you actually need. And so you'll see this. All right, so the pH of the buffer is controlled by two factors, the strength of the acid as represented by Ka, or more appropriately for us in this to see it visually, pKa, and the relative amounts of acid and conjugate base. Like I said, this is just the modifier term. The pKa is the really controlling factor for the pH of the buffer. This just modifies it based on relative amounts present of conjugate base and weak acid. All right, and so let's say you put in equal molar amounts of conjugate base over weak acid. That ratio of conjugate base to weak acid becomes 1. The log of 1 becomes 0, and the pH at that point is simply equal to the pKa. So if you used equal molar amounts of conjugate base and weak acid, you would simply have a solution that has a pH equal to the pKa of that weak acid. If there's more conjugate base, then the pH will be greater than the pKa. If there's more weak acid in the mixture, then there will be a pH less than the pKa. So, preparing buffer solutions. I already explained, that obviously the buffer should control the pH at the desired value, and I explained about how to do that. And it should have the ability to keep the pH approximately constant. And I say the addition of reasonable amounts of acid and base. This is very small. You can overwhelm a buffer, which is called as buffer capacity. That's how much acid and base it can neutralize without changing pH. But it's very easy to overwhelm a buffer by adding too much acid or too much base, at which point, of course, then the pH of the solution will change and we will adopt a new position of equilibrium. But really, physiologically, your body is designed, both your blood and intracellular materials and other places are designed to handle normal amounts of disruption of acidic or basic molecules moving through them without changing their pH. It's only when something goes seriously wrong that you overwhelm the buffer, you've exceeded the buffering capacity, that things really go wrong physiologically. So within reason, in lab, you're going to overwhelm the buffer. But, in normal instances, you would not. All right, so the strategy for making a buffer solution is this. This is not going to be your role here. You're going to just say what is you're going to determine the pH of an already existing system. But if you are going to be in a position where you will create buffers, then here is a strategy that helps you create that buffer. So let's do a couple of lecture problems related to solving buffer problems. Lecture problems 9 and 10. Lecture problem 9 asks you to calculate the pH of a buffer that results when 25 grams of a conjugate base and 8.9 grams of a weak acid are diluted with water to a volume of 2.50 liters. And it gives you the Ka, and it tells you the molar masses, which I would like to say I will do on the exam. I will provide you those molar masses to save you from wasting time calculating those. You should know how to do those. Okay, so when we do this, then we know it's a mixture of a weak acid and a conjugate base, so we know that makes a buffer, and I even said in the problem that it's a buffer. When you hear buffer, your first thought should be the Henderson-Hasselbalch equation, where pH equals pKa plus the log of the conjugate base concentration divided by the weak acid concentration. All we need to do then is fill in some pieces before we can do this calculation itself. All right. So the first thing is let's convert the Ka to pKa because we need this. So pKa equals the negative log of 1.4 times 10 to the minus 4. And this equals 3.85, 387, 1964. And so there's the first piece we need. Now the other pieces that we need are the concentration of the conjugate base and the concentration of the weak acid. All right. So the moles of conjugate base equals the 25.0 grams over its molar mass, which you were told is 112.05 grams per mole. Remember, mass over molar mass gives you moles. And so that gives you 0.223114681 moles. But now we need this to be concentration. And so the concentration of the conjugate base is equal to that 0.223114681 moles over the 2.5 liters. And that is equal to 0.089245872 molar. Now remember, you should be pausing and doing these calculations simultaneously to be sure you're doing them the same way on the calculator and you know how to use your calculator for them. And also remember that even slight differences way out, here in the end of the numbers are irrelevant to significant digits. So, different calculators, being idiosyncratic, then ignore that. Just as long as you've got the bulk of it, you're good. We need to repeat this with the weak acid. All right, moles of weak acid, we were told that we have 8.9 grams over its molar mass of 90.08 grams per mole. So grams cancels, and that gives us the number of moles of 0.098801066 moles. And of course then it's in 2.5 liters, so we take that divided by the 2.5 liters again. And so do that again there. Weak acid, that gives us concentration of 0.039. Whoa. I don't know why it wrote that. It's supposed to be 3. 3952. Oh, I apologize. My screen at this point is difficult to write on. So 0.039520426 molar. Okay. So now we have those concentrations. So get to a new page here to write on. pH equals the pKa value of 3.853871,964 plus the log of 0.089245872 over 0.039520426. And now notice, the amount of conjugate base is greater than the amount of conjugate acid. This means in the end, the pH should be greater than pKa. This result's going to be greater than 1, and logarithm of numbers 1 or greater is going to be positive. It's only the log of numbers less than 1 that gives you a negative number and would make the pH go down. But since there's more conjugate base than weak acid, we should expect that the pH is going to be greater than the pKa. All right, so continuing the calculation, 3.853871, 1964, that's a 1, plus log. Now this result, when you do the division, should give you 2.258221407. And again, if you have slight differences out, many decimal places out, they're irrelevant. So again, 3.853871964, and then the log, that's going to be positive value, 0.353766,520. Remember, the log of any number greater than 1 is going to be positive. All right, and so this gives us overall 4.21248616. Now, again, running back through all the significant digits, for most of that, you had multiplication and division. The Ka had 2 significant digits and you took the log of it, so that means you have 2 decimal places. So the cut, oops, let's go down here. Forget that one up there. So in my raw numbers here at the end, I'm going to have 2 decimal places for the pKa, so 3.85, that makes it significant. Then in my other numbers, 8.9 grams of the weak acid, so that's my limiting part of all of that calculation. That's 2 significant digits, so when I applied the log here to 2 significant digits, that also gives me 2 decimal places. Final operation of addition means that you have the least number of decimal places, but they both have 2, so you must have 2 in your final answer. So the pH of that resulting solution within significance is 4.21. Okay, so that's a simple, straightforward problem, which of course you could solve using ice tables and possibly quadratics and all, but again, why would you when you see it's this straightforward? Okay, so let's do lecture problem 10, and let's clear out 9 here. There we go. And let's look at problem 10. In 10, this is a slight variation of it, of what's being asked, and so it doesn't really change what we're doing necessarily. It just is we're looking for a different piece of the puzzle. Instead of calculating pH, we're looking for a different piece. But still, since what mass of solid sodium fluoride should be added to 1.25 liters of 1 molar hydrofluoric acid to make a buffer, notice the keyword buffer, with a pH of 3.00. So when you hear buffer, you think Henderson-Hasselbalch. So pKa plus the log conjugate base over weak acid. Okay, but now this time, we're given the pH. This time, what we're trying to do is figure out how much conjugate base you need for this. And so we need to do a little bit of work to get there. We already know that the pH of the solution is 3.00. You are also told that the Ka of hydrofluoric acid is 6.8 times 10 to the minus 4, so we need this piece then. pKa equals negative log, and that Ka was 6.8 times 10 to the negative 4. And when you do that, you end up with a value of 3.167491087. All right, so we've got this. Then, and so if we begin working with this, when you see you have 3.00 equals 3.167491087 plus log of, and now we don't know the conjugate base, but you do know the concentration of the weak acid. The problem tells you that you have 1.00 molar of hydrofluoric acid. For the moment, ignore the volume. We don't care how much we have. Its concentration is still 1 molar. And that's all that matters here is the concentration. You could have 20 liters, 1,000 liters and all, but its concentration is still 1 molar. So don't misuse the volume value just yet. Because we understand that concentration is 1.00 molar for the weak acid concentration. So now we have a bunch of values here and one variable. So let's do some rearranging here. What we can do is subtract this out. So we have 3.00 minus 3.167491087 equals the log of the conjugate base over that 1.00. And that's going to give us negative 0.1674911087 equals the log of the conjugate base over that 1.00. Now to get rid of this, then we need to use the 10 to the minus that, and that gets rid of log. And so what we do is when you take the inverse log of that negative 0.167491087, you end up with a simple value of 0.68. And that's going to equal conjugate base over 1.00. Multiply both sides by 1, and you end up with the conjugate base equal to 0.68 molar. Because again, that molar is there. So now, we know we have the conjugate base concentration needs to be 0.68 molar, but we need to do a little bit of work. Because the question itself, don't just write that and that's the answer. So let's continue here. Conjugate base concentration equals 0.68 molar. Because the question itself, you always have to keep in mind, what did the question really ask you for? And in this case, it said, what mass of solid sodium fluoride? That means then grams. When the mass for us in chemistry is going to be grams. So now you know you have 0.68 molar. That really is 0.68 moles per liter. Now you go back to the volume of the solution is 1.25 liters. And that'll give you the moles, which is 0.85 moles. Okay. So now that we know how many moles, we were given the molar mass. So 0.85 moles times the 41.99 grams per mole gives us 35.6915 grams of the sodium fluoride. But as always, you know that can't be the end of the story. And so in this problem, then we look at significant digits and all. And what we find going back through there is that we end up with a total needed number of significant figures of 2. So when we do this, we cut it there. That 6 modifies that 5. This is approximately 36 grams of solid sodium fluoride. So if you weigh out 36 grams of sodium fluoride and you add it to 1.25 liters of 1.00 molar hydrofluoric acid, you will have a pH of 3.00. This concludes Lecture 3.